So I'm going to go through X1 practice exam questions 11 to 15, and they are related to that kind of cross-validation KNN thing that I think they are the most tricky questions from the past exam, because it's so if you know the answer, it's easy. If you don't, it's kind of hard to think why it works. But we'll go through some examples. Hopefully, you'll get the idea uh, behind these. So the first one is asking about if you have a 65 nearest neighbor. So already you probably think it's somehow related to like the total number of examples. And it is actually equal to the total number of examples. And the question is asking what's the accuracy of that. So first, let's see what 65NN will do. So it will, for each of the positive examples, you will find 65 nearest neighbors, which means like all of them, and pick the majority. What is the majority? Negative. So what 65NN does is basically the majority predictor. So no matter what the majority is, just predict that. So in particular, for all of these 21 positive examples, they will all be predicted as negative. And for all of these negative examples, they will also be predicted as negative. Then the question is asking about accuracy. So these ones are predicted correctly, and these ones are predicted incorrectly. So that's our accuracy. So again, once you realize what this thing is doing, then it's kind of straightforward. But then you need to know that 65NN is doing the majority thing. I think a different version of this question is saying, what's the accuracy of 1NN? So if it's 1NN, then it means it just picks the nearest neighbor and predict that. But if you are trying to compute the accuracy on the training set, it basically means you are going to pick the one that's exactly the same and then just label as that. So for example, for one of the positive example, the nearest neighbor is just itself, so we'll predict as positive. So all of them will be predicted correctly. Then we have 100% accuracy. If we do 1NN on the training set. So of course we need some kind of assumption like all of them are unique and so on, but in general that's the case. Okay, so once you see the trick, the next question should be easy. So we have 66 examples, and every time we're going to leave one out and then use the 65 and N thing. So again, this is just the majority predictor. So if we remove one of them, it doesn't matter whether we remove the positive one or a negative one, the majority is always still positive. So if we remove positive one, it's 44 against 22, so majority is also positive. So basically it means we have a predictor that always predicts positive. So when we leave one out, we're just going to, if we leave the positive out, it will be predicted as positive. If we leave the negative out, it's going to be predicted as positive. So these 44 will be predicted correctly, and the rest, 22, will be predicted incorrectly by this leave one out thing. So that's why that's the accuracy. Okay. So I guess now you see the pattern. You have unique data points. So in particular, that means if you have 1NN, the accuracy is exactly 100 on the training set. So again, excuse me, you are randomly selecting a subset of the data from the training set. So they are from the training set. So which means when you pick the nearest neighbor, you will be just itself. So that's why when k is exactly 1, all of them will be classified correctly, which means all 100%. And also the question says your answer should not be dependent on which subset is selected. So in particular, there could be like subsets where 3 and n would predict something wrong, and of course the other ones could predict something wrong. So 1 and n will always achieve 100%. So that leads to the highest accuracy. Right, so the next question is kind of the one that's really difficult from last year. So, excuse me. So we have these letters, and we define the distance just like how you would define it, like how far they are on this alphabet line. And the important thing is that HI, K, L, V, and Y, they are labeled as 0. The other ones are labeled as 1. And the question is asking, what's the smallest number k such that all of them are classified as the same? So it's kind of, if we have the majority classifier, then of course everything will be classified the same. But we want the smallest x. So of course we can have k is equal to 26, then everything will be classified as majority. But we may want something smaller. So first, 1 and n definitely doesn't work. Right, so 1 and n just predict itself. So the accuracy will be 100%, and not all of them are the same. So if you do 1 and n on, say, h, it will just predict as 0, which is different from all the other ones. Okay, so what about 3 and n? If you look at 3, and if you look at maybe either I or j, you can look at I. The 3 nearest neighbors of I are h, I, and j. And 2 of them are 0, the other one is 1, so it will be predicted as 0, whereas, like, it's obvious, ABC, all of them will be predicted as 1. So not everything's the same, so 3 doesn't work. And that's actually how I programmed the autograder, but it kind of, if we do it by hand, it's kind of hard. So in any case, let's, I'm not removing 5. 5, let's see, if we look at j, what are the 5 nearest neighbors? H, I, J, K, L. 4 of them are 0, so we are still going to predict j as 0 now. So most of these are like 1 and j is 0, so not everything are classified as the same. So not 5. What about 7? So we do the same thing with j. Look at j, H, I, J, K, L, M, N. We don't need the N, and G. So these are a 7 nearest neighbor. 4 of them are 0. So the majority is 0. So J is still predicted as 0, while like many of the other ones are predicted as 1. So 7 is not working. So you can probably guess the answer is 9. And the reason, if you look at J, if you move further to include F and N, then now the majority, 5 of them are 1. So J is now predicted as 1. You can actually try all the other ones. You can try H, you can try I, you can try somewhere here, the W, if you find the 9 nearest neighbor, like most of them are 1, so everything will be predicted as 1. So everything labeled is 1. So yeah, so you basically do it by trial and error, and again, it's kind of a tricky question, and that's how you do this. There are no formula, like we cannot like just count the number of consecutive things and then just multiply by 2. That's originally how I implemented the auto grading. It turns out it's wrong, so we do need to do it by like actually going through case 1, 3, 5, 7, and 9 and see which one is the smallest one that works. Okay, so the last question is about k-fold validation. So the number 6, I think based on your ID is different. So in particular, 6 here is kind of a special case where we just leave 1 out. So we will actually do that. And 1 nearest neighbor is finding just the single nearest neighbor. So let's look at the first fold. It's using the first number, and you use the rest to predict this one. And the nearest neighbor, I think the axes are sorted already, so it's very easy to see. So the nearest neighbor is just 0, so I will just label it as 0, so that's wrong. And next, let's get rid of this. So that's why I had. Next, let's leave this one out. And the nearest neighbor of this, compare -8 and -4, is -4. That's the nearest neighbor. So I'm going to predict 0. And for -4, find the nearest neighbor. They're like the same. Let's see the tie breaking rule. So break the tie by using the instance with the smaller index. Okay, so just use the previous one basically. That's 0. And next, 3 is actually closer to 4 compared to -1, so we don't need tie breaking. So that's labeled 0. And -1 is closer to -3 compared to 10, so 1 and 10, obviously, closer to -1. So that's a 0. And now let's compute the accuracy. This is wrong, this is wrong, this is wrong. So the accuracy is 3 right out of 6, so it's 50%.